equation of the tangent plane. We did this last class. And here's the surface. 2 times x minus 2 squared plus y minus 1 squared plus z minus 3 squared equals 10. And the point? At the point 335. Can you find the equation of the tangent plane of this surface? Let me get my answer ready. X minus 3, y minus 3, z minus 5, all equal to 0. Well, what goes here, what goes here, and what goes here? The gradient vector at that point. The components of the gradient vector at that point. I'll do fx here, I'll do fy there, and I'll do fz here, and I'll plug in the points 3, 3, and 5. So let's fx to all that. And I'm talking about, like, think of it just equal to k. So we're just talking about the fx to this portion right here, so you can ignore that equals 10. Just to make sure it's equal to some constant, you're fine. So what's the respect to x there? 4, parentheses, x minus 2. I'll put that here. And what number do I gotta plug in there? At the value x equal to what? Right? What's going here? What's that derivative? 2 times y minus 1 is a partial derivative at the value y equals 3. And then what are you going to do here? 2 times z minus 3 at what point? At the point z equal to 5. And you'll have the equation of tangent plane. Isn't this cool? This is another way to get the equation of a tangent plane. What's this? That's a 4. Is that 4? That's 4. Okay, 4, 4, 4. That's it. There's the answer. There's the equation of the tangent plane. 4, 4, 4. There it is. These are the components of that gradient vector. Of this guy. You just found that's a 4, that's a 4, that's a 4, and you stuck it in front of there. Because that's what's going on when you come on a plane. Yeah, that's the vector that's perpendicular. The gradient vector, isn't that cool? Hey, they do have a part B to this. There's one like this on a practice set, so we might as well do this. It may be a while since you've heard this phrase, a normal line. And we've been always talking about tangent lines. What the heck's a normal line?
Perpendicular.
Okay, that'd be a line perpendicular at that point, tangent, right? So when they want you to get equation of the normal line at this point. So it's been a while since we did lines. Remember lines?
Mm-hmm.
I'm going to put line x equals, I got to do 3 plus something t, y equals 3 plus something t, and z equals 5 plus something t. So what I need, these are the parametric equations of the line. Normal. They wrote line normal to the surface at the point. Well, to be normal to the surface, that means perpendicular to the surface. So right off some surface, I want to think of the surface like this. It's going to run in the same direction as the gradient vector. So guess what numbers I use right here? Use the gradient vector, right? Mm-hmm. If it's going to be normal to the surface, use the gradient vector. Because that's how we do lines, right? Now what is the gradient vector? Is that 4, 4, 4?
Mm-hmm.
There you go. I'll add that right there. And that would be the line normal to that surface right there at this point. The parametric equations of the line. I wrote the parametric equation of the line. You can write in vector form if you want. I think on the practice set there, those practice problems, they are written in parametric form. So you'd be good. Hey, do you agree we could have done this if the surface was a sphere? What's the equation of a sphere look like? X squared plus y squared plus. See, what's cool about this now, this works great when you have z squareds in it. See? I don't know if you noticed this. In the last section, they always wrote z equal. They always wrote z equal to the equation. They always wrote that. So you can figure out that tangent point. Nice. Got raised? Alright. Hey, the last thing we're doing today is section 14.7. Now this is on max values, max and mins. And this is in section 14.7. So 14.7, max and mins. And they give you some equation. How do you get max and mins in Calc 1?
Double derivative, right?
And you all are great. You get the first derivative, right? And it was where the first derivative equaled 0 because the slope would be 0. But now we have functions of x and y, true? So what we're going to do to find max and min, step 1, is we're going to have to find the critical points. Just like you did in Calc 1. Find the critical points. And you go, what's that? Well, you told me it's where the slope equals 0, but now we have an fx and we have an fy. So when that's going to be the points where fx equals 0 and fy equals 0. So we're going to have to find that first. And then there's a second step. You'll love this. So once we get this, these will be the points where there's potentially a max or a min, right? But there's another kind of point. It's called a saddle point. Do you know what I mean by a saddle? Does anyone need me to put it like a saddle? Like, think of the saddle on the back of a horse. In one direction does what? This, and then the other direction can go like this. So that's what's going on with the saddle. So that's another point we can get from our critical points. Critical points when you give us max values, min values, or saddle points. So to determine that, that'll be step 2. We calculate something called the determinant. Now the determinant is equal to this. And I'm going to draw a little matrix here. It's going to be the determinant of that matrix right there. I'll erase this part. We won't need this for section 14.7. We'll get this out of the way. The determinant is equal to, I'll write it really big. This will be step 2 to 14.7. The determinant will be fxx. The determinant of this matrix. What is the determinant of this matrix? Where you go this times this minus this times this. So what does this math formula tell us?
fxx, fyy
Times fyy
minus.
Isn't fxy equal to fyx by Clairaut's theorem? So I'm going to just write parentheses fxy close the parentheses squared. There you go. This will be step 2. Step 2 will be find your determinant. What was step 1? Step 1 was
On the critical points.
find the critical points. Find your critical points. That's step 1. Step 2, find the determinant. Okay, so this is just going to give us a number. Find the determinant at a point. Well, here's the scenarios. And if the determinant, we'll call it D. We're going to call this thing D, all right, everyone? This is D. If D is less than 0, you have a saddle point. So that's easy. If your determinant's less than 0, you got a saddle point. Yeah, but what if your determinant's greater than 0? If your determinant's greater than 0, go check the fxx. And the fxx is greater than 0. Do you all agree that's second derivative right there? Do you all remember about concavity? When second derivative was positive, like concave up, You know what it gives? It provides a minimum. See how I drew concave up? Concave up for second greater than 0. So if the determinant's greater than 0 and f(x) is greater than 0, so I'll put and in here, then you have a local min. Will occur at that point. Let's do another one. And what if your determinant's greater than 0 and f(x) is less than 0? What's happening there?
Local max.
So I'm going to do concave down, second row is negative, concave down, it provides a local max. Or if you don't like the word local, you can think relative max. But let's leave this up. That's a summary of section 14.7. And this is how we'll find our maximums. Or we might find some, I put SP, what's this stand for? Saddle points. That's a saddle point. SADDLE points. Hey, there is one more if you want to add it. What if the determinant equals 0? If the determinant equals 0, then this test is inconclusive. Could be a max there, could be a min there, you'd want to investigate it some other way. Like use technology or something. Use Maple, make the graph, right? Look around that point. So if you do get some point where the determinant came out to be 0, I didn't want you to think, does that mean something? It means this test is inconclusive there. Cool? So if you want to add that to this, you can. If d equals 0, here, I'll put it right here. I got a little room. And when if d equals 0, it's inconclusive, right? This whole test. We're going to explore that next, and whatever that one's going on here in some other way. So here's our first problem. Here's a function of x and y. How about x cubed minus 27x plus 3xy squared? The question is, can you find the critical points and find all local maximum and minimum values and saddle points for the function? So this is in 14.7. Find all local min, local max, and saddle points. This graph. You all know what I mean by a saddle point?
Determinant, right?
Yeah. So what's step 1?
You have to take the
Very
derivative.
So let's find the critical points. Set fx equals 0 and set fy. Well, what's fx? Hardest part of the problem. What do you get for fx there?
3x squared
3x squared
minus 27
minus 27
plus 6y
plus 6x
6xy, sorry.
plus 6y squared.
6y squared, yes.
Is that the derivative with respect to x?
No, 3
Plus 3y squared.
3y
Love it.
squared, sorry, yeah.
You're the best. Equals
0.
0. I'll put a big wall. Now don't forget, and what else we need to figure out?
Fy.
Which is 6xy equal to 0. Okay. But we got to solve this daggone system. This is the only hard part to section 14.7. Can you help me solve this system? And once we solve this system of equations, we'll have our critical points. And from there on, it's just going to be straightforward, just plug it into this little math formula to see whether you got local max or mins. But we're going to solve this system. So how do you solve the system equations? We go to one equation. There's 2 of them here, right? Pick the one that's easier. I think this one's easier. Do you agree? I pick the one that's easier. I solve for one variable, then I plug it into the other one, right? And see what we get. So let me start out. And if 6xy equals 0, what would x have to be?
0.
So if 6xy equals 0, then you're telling me if x equals 0. So when x equals 0 is one possibility, right? Now don't forget, we're gonna get what's going on with x equals 0. Don't give up on the problem then. We also have to explore what was the other option. What else makes it 0?
Y.
So we'll come back to that, okay? But let's start with if x equals 0. So if x equals 0, we plug it over here. We're trying to find our critical points. I get 3 times 0 minus 27 plus 3y squared equals 0. Can you solve that?
Y equals plus or minus.
3.
Way to go! Not just 3, but
Plus or minus.
Yeah, plus or
y squared equals 9 and y equals plus or minus 3. So I'm gonna get my list ready. Let's call them the CPs, the critical points, or the critical values, right? Looks like we got 2 already. X is 0, what is y? 3? What's the other one? X is 0 and y is?
-3.
Cool. The worst part is on the test is it's like people just stop there. Like, all right, but we can't forget, we didn't explore what?
X.
The only tricky thing about a system of equations with 2 variables, I'm going to come back here and go, wait a minute, what else could it work?
If y is 0.
If y equals 0, this works. So we explored this. Now what if y equals 0? Maybe we can get more critical points. You never know how many critical points you're going to get. 2, 4, 6, 0, sometimes it's 0. What if y equals 0?
Same thing, x equals to plus minus 3.
So 3x squared minus 27 plus 0 equals 0. I got you. Then x equals plus or minus or what? 3. So let's list those. Y is 0 and you get... Yeah?
Professor,
Cool.
that derivative of f of x is actually circle. If you look at it, you can do it that way also.
That derivative of the...
Yeah, because it forms a circle. 3x squared minus 27 plus 3y squared. And if you divide by 3, it becomes x squared minus 9. But in that way, you can also find it out also, you know?
Oh, right. Very good point. Factoring out of 3?
Yeah.
Yeah, because it's equal to 0. He says, because this is equal to that, you can definitely do that. Very good. I like that.
Thank you.
All right, now everyone, what are these? Maxes, mins, saddle points. So I'll erase all this. We got our critical points, right? There were 4 of them.
I will find the determinant.
Let's go to the determinant. Oh, great, I just erased fx. I needed that to get fxx, don't I? What was fx again?
3x squared minus 27
Is that it?
plus 3y squared.
Plus 3y squared. There's fx. And fy is just this what? In order to do this determinant, look what I need. I need fxx, and I need fxy, and I need fyy. So what's fxx?
6x.
6x. What's fyy? What's the derivative of that with respect to y? 6x, nice. And what's fxy? Remember, you can do fxy, or you can do fyx. I'll do fyx. I get 6y. fxy is also what? Do you all agree? fxy is the same as fyx. You can do either one of those to get that. I do them both just to make sure I did it right. All right, let's put it in the formula. What is it? Determinant equals fxx, fyy, minus fxy all what? Squared. So this is 6x. fyy is 6y minus 6x squared. So far, so good. Hey, you want to write this again? Might as well. What is that? 36xy? Go ahead.
Isn't FYY 6x
Oh, you're the best. What was that? FYY right there is a... And what was this again? Just 6x, right? So this will become 36x squared, thank you so much, minus,
That should be 6y.
oh, this is the what? I had these switched around, I apologize, everyone. So 36x squared minus 36y squared. And this is the determinant. What do we do with all these points? Plug them in. All right, you ready? 0, 3. What happens with the determinant?
That's negative.
So guess what it is? I'm just gonna put SP for saddle point. There's a saddle point at the point 0, 3. How about 0, -3? Determinants also what? I love saddle points. Because you don't have to do anything else. It's the other ones you gotta do more. Is it negative again? Yeah. Saddle point. How about 3, 0?
That's positive.
Alright, now these positives, so we gotta go back over here. So we gotta retain this, and what I always do is, I'm gonna forget this on the test. I just think of concavity. If determinant's positive, second derivative positive be concave up, that didn't give me a minute. So when you go back in here, here's the fxx. At 3, 0, what's going on with this fxx right there? I'll put a big yellow marker on it. What's going on here?
That's greater than 0.
fxx is also what?
Greater than 0.
Greater than 0, so what's going on at 3, 0?
Local min.
There's a local min. I'll just put min. You can just put min if you want, local min. What's going on at -3, 0? Determinant's positive, isn't it?
Mm-hmm.
But what's going on at fxx?
Local max.
fxx is less than 0, give me a
Local max.
local max. Cool. Hey, it's okay for me on the test if you say there's a local min here, local max here, saddle points here, or just write it like I just did here. But you will see, like in the textbook, if they talk about what the local max is, that wording, the local max of f is, you know what they would say? They gotta plug these two numbers here back into the what? The original function. Do you all agree? If you use the verb is, you're talking about the z value. Right? You're talking about z value. So if you wanted to write it like that, the local max of f, it occurs at 3, 0, but what is it? You'd have to plug -3, 0, you have to plug the -3 and a 0 back into the original function. Which, is it easy to do? It's not bad. What would it be? I'm just curious. Local max of f. It occurs at the point what? -3, 0, and is, you want to help me plug this in? Just in case someone's curious. It would be, what's -3 cubed?
-27.
-27.
Plus,
Then-
plus 81.
Because -27 times a -3 is plus 81, plus 3 times,
That will be 0 actually.
that's just going to be 0. So what's that all that come out to be? 54?
No.
But you don't have to do that. You can, what I'm saying for me, I'm just to save time, you're like, hey, there's a local max occurring here. There's a local min occurring here, and you got 2 saddle points at these points. Cool. Hey, awesome. And I'll make sure even tomorrow when we start, let's do another one. Let's do another one. Because this one, everyone, great problem, but I want to make sure when you do the practice set, and feel free to do it tonight, that you can do one like number 22 plus. I didn't do one like number 23. Which is the application of this. Have a great day. See you tomorrow. Hey, so we'll be great tomorrow. Everyone, we just got to finish up. Do a couple more 14.7s and 14.8. Isn't that cool? So there'll be definitely time for what? Any last questions about practice sets? Unless you want to bolt early. 14.8 won't take the whole time.